tube with nanomanipulator and get this very thin and uniform monocrystal, which we typically call nanoneedle. Nanoneedles have huge aspect ratio, so their lengths go up to 70 microns and diameters are between 10 nanometers and 1 micron. Well, it turned out that those nanoneedles are very strong, have almost ideal cylindrical shape. Obviously, they're not cylinders. They have hexagonal structure but can be easily approximated as cylinders. They have ability to recover their shapes after deformations above 50% and respond to very small forces, which makes them excellent candidates for all sorts of force sensing of soft materials. And this is the obvious application we started using recently. This is an example of AFM force distance curve. This is basically testing of mechanical properties inside atomic force microscope. And we tested it once after the synthesis, this is blue line, and then after, let's say, 50 experiments with different deformations, we repeated this experiment under the same conditions and we found the deviation is less than 4%, which basically means that needle recovers completely. This deviation most likely just because of defects on the surface. It's not because of deformation of the needle. So our needle passed the test to be a physical tool, so now let's use it as a tool. Well, to use it as a tool to measure forces, we're going to use it exactly like we use, let's say, springs at macro scale to measure forces. The only difference is nanoneedle by itself, it's not a linear object like a spring. With springs, everything is straightforward. F equals K delta X. Large deformation of needles are nonlinear. So in general, we expect nonlinear response. So force is not directly proportional to the deflection. And another thing is to calibrate the needle, we cannot use any approximation of small deformations because our deformations are not small. They're huge. They're about 50%. So how to calibrate the needle? By calibrating the needle, I mean direct correspondence between the force and deflection. So we deform it, and from this deformation, we want to know what is the force applied to the needle. To calibrate it, I was using very nice and elegant mathematical model, which is called generalized elastic approach. It allows you to solve a nonlinear equation, equilibrium equation for large deformation of the beam in terms of elliptic integrals. Elliptic integrals are standard functions, just like Bessel functions, for example. And these elliptic integrals can be easily calculated numerically using computer. So but obviously, when we calculate the shape, we don't know one parameter. We don't know Young's models of this needle. And this is a significant parameter for measurements. If you don't know Young's models, your shapes will be, for the most part, arbitrary. You don't know if it's a real shape or not. So here, for example, this is deformation of the needle, again, using nanomanipulator and SEM on the hard surface. So you see that dashed blue line is basically a reconstruction of the shape using generalized elastic model for, again, arbitrary value of Young's models. But we don't want to use arbitrary value because it gives a variety of different solutions for our shape. We want one strict solution. We don't want any multiplicity of our functions. So in order to do that, I did the following experiment. We reproduced the same experiment in atomic force microscope and in scanning electron microscope. So scanning electron microscope allows us to reconstruct force distance curve. What is force distance curve? Basically, normal force versus deflection. It's very simple. It's just the same as force versus delta x for the spring, if you stretch a spring. So for nanoneedle, experimentally, we obtain force distance curve in AFM, which is this blue line. Then we go back to our SEM imaging and fit shapes, experimentally obtain shapes with generalized elastic model. If chosen value of Young's models, which is arbitrary at this point, is too high, see, theoretical force distance curve will go above experimental. If it's too low, it will go below. But if the chosen value is correct, so it required some work from me, it will be exact fit between theory and experiment. And this is the way to find Young's models of this nanostructure, which is 68.3 gigapascal, which is a reasonable number because it's comparable with the Young's models of silver. So now our needle is fully calibrated. It's a calibrated tool. We know all the mechanical properties. We can start measurements. And this is preliminary measurement we performed with this needle. So this is an array of brush-on polymer fibers on silicon pillars. Typically, it's very hard to target those kind of fibers with any kind of tool, except our needle will work very well for them. So principle is very straightforward, how to find Young's models. Young's models, by definition, is stress versus strain. Tension can be found from the normal force. Normal force can be found from the deformation of the needle. So we know this T, which is tension of the fiber. The most interesting thing that my teaching presentation today was about tension and ropes, and this is one of the practical applications of this class. So this is again about tension.
Where does that polymer fiber occur, and what type of device is that occurring?
You mean practical application
yes,
of it?
Yes.
This is for people required for tissue engineering. So these polymer fibers are useful for all sorts of bioengineering, in particular tissue engineering. And bioengineers, they would like to know what are the mechanical properties of these fibers for tissue engineering. And all the other parameters here, like relative elongation and radius of fiber, then they can be found from imaging. Okay, so that's the way, like very elegant way to use nanoprobe for Young's models of polymer fibers. And this is again buckling of needle in the polymer fiber and reconstructed theoretical shape of elastic curve. And we found that the value of Young's models is 296 gigapascals, which is a very reasonable number. It's the same as for polymer fibers obtained by electrospinning, published before result. So people in nanotechnology loved our paper a lot, so they put it on the front cover. It's like published last month, January 2008. And if you want to learn more about that, please Google nanoneedle as a force sensor. It will give you a lot of information. Most likely the first link you will find is this. This is like a short article for broad audience about this kind of sensors. This is the company, nanoneedles LLC, which, funny name by the way, which makes this kind of probes. It was founded recently at the University of Louisville by a good friend of mine, and it's partially based on my studies, so you will find out lots of references to my publications and articles over here on the website of this company. Okay, so that's all about nanoprobes, mechanical nanoprobes. Now I just mentioned